Example 17.2. In this example, we have a glass window which has a cross-sectional area of 0.8 meters by 1.5 meters. It has a thickness of 8 millimeters and a thermal conductivity of 0.78 watts per meter square Kelvin. This window is located in between the room and the outside. The inside of information of the room is that it's maintained at a temperature of 20 Celsius and it has a heat transfer coefficient of 10 watts per meter square Kelvin. The outside is maintained at negative 10 Celsius and it has a heat transfer coefficient of 40 watts per meter square Kelvin. Both of the heat transfer coefficients include the effect of radiation. We're going to assume this problem to be steady, one-dimensional, and it has constant properties. In order to solve this problem, we're going to use thermal resistances. So we're going to use three thermal resistances. The first resistance is going to be a convection resistance that it takes place between the inside of the room to the wall, so that's going to be convection. There is going to be conduction that takes place inside of the glass, and then there is going to be convection from the wall to the outside temperature. So we're going to start with the first resistance, so we're going to call it Ri, and simply for the resistance in the inside, and it's going to be a convection, so it's 1 over HIA. Okay, and then we substitute the values and we find that this resistance is equal to 0.083 Celsius over watts. The second resistance is going to be the resistance of the glass, and once again is going to be a conduction resistance. This is going to be the thickness of the glass divided by the thermal conductivity and its cross-sectional area. Once again, we substitute all the values and we find that this particular resistance is 0.0085 Celsius over watts. And then the last resistance is the resistance that we have for convection for the outside, so it's RO, and is 1 over HOA. And once again, if we take all these values and substitute it, we find this to be 0.02083 Celsius over watts. Okay. So what we're looking for is the amount of heat transfer throughout the whole system. The temperatures that we know in this moment are the temperatures from the inside and outside, the T infinities. So we could say that the rate of heat loss is equal to the delta T divided by the resistance that joins these 2 points. The resistance that joins the 2 points that we have in this case is going to be, so it's a total resistance, and this total resistance is going to be the addition of Ri plus the resistance inside of the glass plus the resistance on the outside. So basically the addition of the three resistances we calculated previously. If we find this addition, we find that this value is equal to 0.1127 C over W. And now in order to calculate the value of Q dot, we write the values that we know, the temperatures, the notes of the temperatures are going to be T infinity 1 minus T infinity 2 divided by the resistances that take place in between those two notes, which is as we calculated the total resistance. We substitute all those values and we find that the value of the rate of heat loss is equal to 266 watts. A couple of things that are important for you to see for the result. One, notice that the value of Q dot is positive, and as we expected, we found the value is moving from T infinity 1 to T infinity 2 because we know for the second law of thermodynamics, heat goes from high temperature to low temperature. Another important thing to realize is the value of the Q dot is exactly the same that goes through every single one of the resistances. That value has to be constant. Remember, if Q dot it is not constant, then you will not be able to use thermal resistances for your application. So now, using this information, let's calculate the values of T1 and T2. We're going to start with T1. And for that, we're gonna use the same relationship. We're gonna say that Q dot is the same Q dot for everybody. It's between T infinity 1 and T1. And we write the resistance that is in between those two nodes, which is going to be equal to Ri. If we solve for T1, we simply find that T1 is equal to T infinity 1 minus Q dot and the resistance on the inside. And then we find that T1, it is equal to negative 2.2 Celsius. So now let's do the same process to solve for T2. So for T2, you could do either T infinity 1 to T2 and add R inside and out of the glass, or you could go from T2 to T infinity 2 and use RO. So we're gonna use the second choice. We're gonna go from T2 to T infinity 2, and we're gonna divide by RO, which is the resistance in between those two nodes. Once again, we solve for T2. We find Q dot RO plus T infinity 2, and then we find that T2 is equal to negative 4.46 Celsius. Now let's talk about the temperature distribution that we got. So the T infinity that we have in the inside was equal to 20 Celsius, right? And then we went to the wall. The wall has a temperature of negative 2.2 Celsius. Then the other side of the wall, the outer surface, it has negative 4.46. And then the final temperature of the outdoors is negative 10 Celsius. So you could see that you have a decreasing temperature as you move along. And that is exactly what we want. We want the heat to go from high to low. So you had to see a decreasing value of the temperature. Another important thing is notice how the difference in temperatures are between the nodes. Notice that the highest delta T that you're gonna have is going to be in your first section, in this part over here. Notice that it goes from from 20 to negative 2.2. So we have about 22.2 Celsius of difference. That is the highest amount of delta T that you have. And if you notice, that is proportional to the resistance. The higher the resistance, the higher the amount of delta T that you're going to have. So if you see from the relationship over here, we could see that the resistance times the value of Q dot is equal to delta T. So we could say that the resistance and delta T are proportional to each other. And so notice that the lowest resistance that we have is going to be in the glass, and that also shows the lowest amount of temperature difference between the 2 points.